So now we're going to start looking at, we've talked about moisture, we've moved stuff around in the atmosphere, so we're going to talk about clouds, precipitation, and really how we can see precipitation with the radar. So let's see if we can get moving along here a little bit. So how do clouds and precipitation form? Well, we learned that water vapor, air can only hold so much water vapor before it has to condense. Interestingly, there has to be cloud condensation nuclei for that to happen. And these cloud condensation nuclei might be from volcanoes, might be from erosion of soil, forest fires, maybe sea spray. There are even domestics, such as chimneys or exhaust pipes, might put condensation nuclei in there. So look at the difference here. Here's the size of a raindrop. Notice how big it is. Here's the size of a cloud droplet. And then inside that, teeny tiny, would be a cloud condensation nuclei. So why the heck do we need these condensation nuclei? Well, interestingly, this wonderful curve on the cloud here means that that little droplet can lose those molecules much easier than it could on a flat surface. So because it's so sharply curved, because it's so tiny, it takes a tremendous amount of water, supersaturated air, in order to make that continue to be saturated. Literally 300 to 400% relative humidity. We don't get that in the atmosphere. But those cloud condensation nuclei dissolve in that little tiny raindrop, and they dissolve in a way that bonds those molecules together so the raindrop stays whole, and the saturation of it only needs to be at about 100% or even slightly less. So that's the purpose of a cloud condensation nuclei. Without it, we would be really, really pressed to have clouds in our atmosphere. Now, once you get a cloud condensation nuclei in there and it begins to form this little tiny cloud droplet, well, more cloud droplets can form around it, and eventually they're going to be able to form rain. Excuse me. However, guess what? These tiny little rain cloud droplets don't become ice easily. Literally, without any dust or debris or anything in the atmosphere, you can't get any ice to form on these cloud droplets until it's at least minus 32 degrees Celsius. That's cold. So how the heck do we get ice? Why do we have snow at 32 degrees Fahrenheit? So what happens is there's ice nuclei. Very similar, slightly different than what we have for the cloud condensation nuclei. And when they get into a cloud, they allow ice to begin to form, usually at around minus 9 degrees. So clouds are super cool. Remember, they're raindrops. These cloud droplets are made of liquid, so they're going to move a lot more. Once they begin to get frozen, they don't move as much. But in these tiny little raindrops, this kinetic energy can inhibit that. That's why they're able to grow bigger. That's why they're able to get colder than their surrounding air. Eventually, however, precipitation does form. And when it does, think about it. The air is moving up. There's friction. We've already learned about friction in the air. And the air is moving upward. So why the heck would these cloud droplets want to come to Earth? Well, they get heavy. Gravity pulls them down eventually. And eventually that allows them to come in a straight line down right towards Earth. So one other thing with these ice condensation nuclei, almost all precipitation that begins on our Earth is formed through ice. In other words, the air temperature gets cold enough and those ice condensation nuclei form that they begin to freeze all these little tiny water droplets in the cloud. And we've learned in the last time that saturation vapor pressure over ice is lower than over liquid. So guess where the water is going to flow? Towards low pressure. So the ice crystals grow at the expense of the water. So the ice crystals are the ones that become the dominant in the cloud. And that, most of the time, is the Bergeron-Findyson effect, the collision coalescence effect. All the cloud is above freezing, and the droplets just bend to collide with each other, and they begin to get bigger that way. You can see it here, like a little raindrop hits another raindrop, and eventually they get big enough that they begin to fall to earth, and we have rain. And that happens in the summertime up here, in the tropics, a lot of the time. Hurricanes, big example of it. Many hurricanes are very warm. However, on this one, the Bergeron-Findyson effect, we get the cold water up there, we freeze it. The ice continues to grow, and gradually the ice gets so big, it starts falling as snowflakes. And eventually, almost all the liquid cloud droplets and all become frozen. They fall to earth as ice, though. So why don't we see ice all the time when outside? Well, temperature is above freezing, so most of it melts. Here's just an example of Virga, and I saw a lot of that on a westward trip here. What happens is the relative humidity below the cloud is very dry, maybe only 20-30%. And here's this cloud dropping precipitation into it. Water does evaporate with time. So what happens is most of the precipitation evaporates before it ever gets out of the cloud. That's why out in the West, sometimes they'll get thunderstorms that have lightning in them, but no precipitation. Here are some of the precipitation types. You see rain compared to drizzle is much bigger than drizzle. And they typically form like a teardrop. Not quite. They're flattened surfaces. Here are different types of snow. You think it's hard to forecast snow just by, how much precipitation is going to fall. Well, there's another complicating factor to snow. Snow can form as these platelets, if it's very, very cold, or columns, or not so cold. They can form kind of similarly. But here there's dendrites, and here there's dendrites. Well, these dendrites are very fluffy, very big. So the same amount of precipitation as a dendrite, with a dendrite snowfall, might give you 5 or 6 inches. If, on the other hand, you had these prisms or needles or whatever, you may only get 2 or 3. 5 or 6 is a whole lot different than 2 or 3 as far as how your driving goes and what's going to happen. So that is part of what is taken into account when you're forecasting snow. And here you can see, typically, the precipitation in the Bergeron-Findyson is all snow as it starts. As it's falling down, it hits a warm layer. And that layer melts the snow to liquid. As it's falling, if there's another colder layer near the surface, well, then that may become sleet, freezing back up as the ice because it's deep enough. Or if it's just cold at the surface, we get that freezing rain, which everybody hates. At least I do. And then if it had stayed cold all the way through the column, then you get snow on the ground. So you can see the temperature aloft regulates what you're going to get at the surface. And here you can see what we call a typical freezing rain sounding, where it's quite cold at the surface and quite warm just above the surface. I had freezing rain when I lived in Sterling once. The temperature was 15 degrees. However, about 1,000 feet up, it was plus 3 degrees Celsius. So you can see, wow, it doesn't take a lot to melt the snow coming down, but can really get icy very quickly if it doesn't. All right, so radars are a way of looking at this rain. What they are is we send a microwave pulse out and we listen for a long time. Believe it or not, these emissions from a radar are less than what you get even from your own microwaves standing by them. Unless you're directly in a radar tower where the radar is rotating around and hitting you, you're just not going to get that much from this. These are very tiny amounts of radiation going out. And they reflect back, either velocity, and that's from the Doppler effect, or reflectivity. And you can see here the radome and WSR88Ds. And the Doppler effect allows you to see motion, detect it, so you can tell which way the particles are moving. The reflectivity part picks up basically raindrops, but it can also pick up dust or even bugs sometimes if you're a high enough concentration. I have seen lines of bugs along a cold front where there's no precipitation, but the bugs have been pushed in together. And if you were to watch a cold front, there's actually more bugs right along it than there is outside of that area. Here you can see dual pole. And dual pole is a big upgrade that occurred several years ago now. What it does, we'll look at that in a minute. We'll just go there for next. So with that in mind, I wanted to show you first the total precipitation across here. This is just total precipitable water. Currently, you can see there's a lot along the east coast of the United States, a little bit up here, but more in the tropics and the intertropical convergence zone. But let's see if we got any radar ever working here. I'm not a big fan of the National Weather Service radar maps, to say the least, so we'll look at dual pole in a minute. Dual pole is a horizontal droplet that goes out signal, and it also has a vertical pulse, so you can detect the shape of a particle. That's key. Think about it, not all rain precipitation is exactly the same. Snow is going to be a different shape than a raindrop. Hail is going to be a different shape than any of those. How about if a tornado occurs and it pulled debris into the sky? That's going to be a different shape. So that's where dual pole radar really helps us. If you're looking at differential reflectivity, here is a normal reflectivity of hail. If I didn't have dual pole, this is what I would see with hail. But if I do have dual pole, this is what I can actually see by looking at differential reflectivity. All differential reflectivity is telling me how much change there is in the precipitation shape. Notice it's fairly uniform around here. Bigger drops maybe down in here. But right in here, it really changed. Something caused it to change. What happened? Well, it corresponds with very heavy precipitation. That is hail. So while we may not be able to tell the size of that hail for sure, we now are able to differentiate hail from rain. Kind of cool. Another thing I wanted to show you, if I can differentiate one type of precip, maybe I can differentiate others. So looking at, again, how similar are the precipitation. Here we see a line of showers and other steadier rain back in here. This is the melting level. Well, what happened here? Everything was snow out here. Everything is rain right here. Guess what? Where they're melting, you have a mixture of the two. You have different shapes, and you get to notice that by this correlation coefficient. And if you have updrafts, think about it. You're pushing warm, moist air upwards. You're shooting big particles of water vapor, water upwards, the raindrops. So you wind up mixing raindrops with ice up in these where the strongest updrafts are. Kind of neat. So radar has a lot of uses. And remember, this is dual pole. This is not phased array. Phased array is a very different radar. So let me know if you have any questions about this.